Okay, so welcome to this first lecture. We'll be looking at the classical linear regression model. It's based on chapter 3 in the textbook Introduction to Econometrics for Finance by Chris Brooks. Okay, so what is a regression? Regression, first of all, it is the single most important tool at the econometrician's disposal, right? It is the major econometric tool that is used by researchers basically to determine the relationships between several variables. So essentially what it does is look at the effect of at least one variable on another variable, or the effect of several variables on a particular variable. Okay, so it's an attempt to explain movements in a variable by reference to movements on one or more other variables. So in this case, for regression analysis, we denote them by x and y. So what regression analysis does is look at to what extent does the variation in y, or what extent is the variation in y explained by the variation in x, or to what extent is the variation in y explained by the variation in several x variables like x1, x2 up to xk. Okay, where there are k independent variables. So now we have to pay attention to the terminology here, right? Y is called the dependent variable, okay? Because we want to know what is the effect of several other variables, the x variables, on y. So y is known as a dependent variable, okay? It's also known as a regressand, the effect variable or the explained variable. X is known as the independent variables, the regressors, the causal variable or the explanatory variable. Okay, so we're looking at how does the behavior of x explain the behavior of y, or how do changes in the behavior of x explain the behavior or changes in the behavior of y. Okay, so of course you can have many x variables, right? But for the purpose of this lecture for now, we will limit ourselves to the case where there's only one x variable to start with, right? So let's say we want to look at the difference between regression and correlation, right? If we say x and y are correlated, all it means is that we're treating x and y in a symmetrical way. In other words, we're not looking to see how x affects y, right? All we're looking to see is whether there's some kind of a relationship between x and y. So in other words, let's say you were to plot x and y on a graph, right? The data for x and y variables on a graph. You may find that they have some kind of a linear relationship, right? In that they may move in a very similar pattern over time, right? Or they may move they might move in the same direction over time, or they may move in the opposite direction over time. Okay, so that means they might be positively correlated if it is their pattern when you plot it on a graph is very similar, or they might be negatively correlated if it is they look as though they move in the opposite terms, in opposite direction. Okay, but it doesn't mean that x causes y. It's not looking for that kind of relationship or causality relationship. All it looks at is whether there's some kind of a linear correlation or linear relationship between x and y in one way or the other. But in a regression, however, we look at the effect of the independent variable or variables, the x's, the effect of these x's on y. How does x affect y? That's what the difference between a regression and a correlation would be. The y variable is assumed to be random or stochastic in some way, right? Meaning it has a probability distribution. And the x variables are assumed to have a fixed or non-stochastic values in repeated samples. So let's look at a simple regression. So we say k is equal to 1, meaning that there's only one x variable. Now, k denotes how many x variables we have, or how many independent variables we have. So in this case, we're saying that we only have one independent variable. So we say k is equal to 1. So we look at the effect of how only one x variable affects y, right? And examples of what this might be in finance. So how do asset returns, like stock returns vary with their level of market risk? How does risk affect returns? Or how does the long-term relationship between, what is the long-term relationship between stock prices and dividends? Or we could look at constructing an optimal hedge ratio. So let's look at the theory behind the regression, or behind how X affects Y. Okay, what this looks at here is it plots on a graph the linear relationship between X and Y. As you can see here, Y on the vertical axis, X on the horizontal axis, right? And what this is showing us is that as X increases, Y increases. So an increase in X leads to an increase in Y. That's why when you plot the data in this graph, right, it slopes upwards from left to right. So that shows a positive linear relationship between X and Y, suggesting that an increase in X causes an increase in Y. Okay, now we can use the general equation for a straight line to get the line that best fits the data. And this terminology is quite important to remember, right? Because the regression is simply looking, the regression, when you plot it on a graph, it looks at, right, the regression is an equation then that shows how the data is fitted, or that fits the data. So the researcher, this of course here, y is equal to alpha plus beta x. This is the equation of a straight line, right? So this is the equation for a straight line. Y is equal to a plus bx, right? And what we want to do is find the values of these parameters here, alpha and beta, okay? And when we work this out, we would be able to place the line as close as possible to all of the data points taken together. So if we assume this equation is appropriate, if the values of alpha and beta are calculated and given a value of x, it would be possible to determine with certainty what the value of y is going to be. Okay, so statistically, it would suggest the model fitted the data perfectly, and that is all of the data points lay exactly on a straight line, right? But this is not realistic. So what it tends to look at is like this. You draw the regression equation, right, which is this. This would be perfect if all the data points were actually fitted on this line, but as you can see, it's not. So the new regression term to denote this picture is y is equal to alpha plus beta x plus u being the random disturbance term. This means that, well, it implies that all of the data points are not on the regression line, which means that the regression, even though it does fit the data or explains how X affects Y, right? It does not 100% accurately indicate or perfectly indicate all the time how X affects Y, meaning that there are other factors, first of all, that would, or other determinants that would affect Y besides X, besides this particular X variable, right? And we might have left it out. Hence, it shows the linear relationship moving upwards from left to right, yes, but it's not perfect. So there may be also errors in the measurement of Y that can't be modeled, or random outside influences on Y, which we cannot also model, okay? The most popular reason for this disturbance term U is that this is not going to tell you everything about Y. So you may find that taxation is not going to, let's say X is taxation. We're looking at how does taxes affect the sales of a particular commodity in a district. So, but taxes is not the only variable that's going to affect sales, right? Prices will affect sales too, but it's left out of this equation. So that effect is going to be captured by the random disturbance term, or the error term, as it's also frequently called, UT. So how do we determine what alpha and beta are? Okay, so to determine what alpha and beta are, we choose alpha and beta so that the vertical distances from the data points to the fitted lines are minimized. Okay, so that the line fits the data as closely as possible. Right? We're not able to get all the data points on the straight line. but you're looking for the line that fits the data, or that can accommodate to these data points as closely as possible then, right, on this line. So to do that, to estimate the regression equation, we use a technique, a very popular technique known as ordinary least squares. Okay, this is the most common method that is used to fit a line to the data. Okay, or in other words, to estimate this regression equation. It takes each distance and square it, right? So for example, as you can see, I mean, this is quite self-explanatory. You take the area of each of the squares in the diagram and minimize the total sum of squares. Hence, you call it least squares. Okay? So if you want to tighten up the notation, we let y denote the actual data point at time t. Okay? And y hat at time t denotes the fitted value from the regression line. In other words, what is the fitted value? It means that, let's say we don't know what y is, right? But we know what the regression parameters are. We can use the regression parameters alpha and beta here to work out what y is going to be. But it may not be exactly that particular data point of y. It may be, well, that's why you call it a fitted value. It's an estimated or a forecasted value of y using this regression line. So that's why we say it's a fitted value from the regression line using the regression itself, right? And this regression equation is depicted by this line, just to recap. But if you know the values of alpha and beta, and of course you know what x is, because this is what you want to use to explain how y behaves, then if you don't know the values of y or the future values of y, you can use the regression equation here to determine or to forecast or what the value of y is going to be. That's why we call this y hat, or the fitted value of y from the regression line. Okay? Right. And we can let, it's not written here by in error, but we can let if we put u and we put u hat instead, right? U hat denotes the residual, which is the difference between the actual value of y and the fitted value of y, right? We call that u hat. So the point in ordinary least squares is that we want to minimize the sum of squares, the residual sum of squares, or the sum of squares error. Okay, because remember, this is known as the random disturbance term, or the error term. So if we were to square this and sum it, right, that would be known as the sum of squares. But we want to minimize this as best as possible, because when you minimize this, it means that the regression itself is a better fit of the data, right? So we want to minimize the sum of squares of the residuals, or the errors, the disturbance term. So that'll be the sum, the square of the first residual plus the square of the second residual, the third, fourth, and the fifth, right? And again, u hat is the difference between the actual point yt and the fitted value of y. Okay, so we want to minimize the sum of squares of residuals, and that's why we use OLS, because OLS is a technique that is used in estimating a regression equation to minimize the sum of squares of the sum of squares of the residuals. Okay, so minimizing the sum of squares of the residuals is equivalent to minimizing the sum of y minus y hat squared, because y minus y hat squared is this in itself, y minus y hat, is a disturbance term, the random disturbance term. Okay, now how do we go on to estimate alpha and beta? The equation for alpha would be, or the fitted, now we call this a fitted value of alpha because it's an estimate of it's the estimator then for the value of alpha. So the estimator for the value of alpha will be the average of y, the average of the dependent variable, minus the estimator for beta times the average of the independent variable x, where beta hat, the estimator of beta, is equal to the sum of xt, which is x at time t, t being one. Now t denotes a time notation. It could be, let's say your data set is daily data, so t would be today, tomorrow, let's say Monday, Tuesday, Wednesday, Thursday, Friday, etc. Right? And if T were monthly data, then it would be each month, January, February, March, April, May, and so on. And T could be annually too, right? Going from one year to another chronologically. So this is the sum of x minus xt minus the mean of x times y at time t minus the mean of y divided by the sum of x at time t minus x, the mean of x all squared. Okay, that's how you determine beta hat. And OLS, which you do on your on the Econometrics software, which is a click of a button, it gives you the value of alpha and beta. So you don't actually have to go and work this out by hand. Now, by construction, OLS finds the parameter values of alpha and beta that best fits the sample data. Okay, any other parameter values will lead to a worst fit and a higher sum of squares of the residue of sum of squares of the disturbance too, or the residual sum of squares, RSS. So let's take a look at this example here. Let's say we want to have the following data on the excess returns on a fund manager's portfolio, right? And this is the portfolio, together with the excess returns on market index, on the market index. We're looking at how does the excess return on the market index affect the excess return on the portfolio. In other words, how does the market risk premium affect the portfolio risk premium? Because you can see here, this is the market return minus the risk-free rate. RF is the risk-free rate at time t, right? This is the portfolio return, RXXX at time t, minus the risk-free return at time t. This is the risk premium, okay? On the portfolio, this is the risk premium on the market portfolio. So we want to see how this excess return on the market index, which is X, affects the excess return on the portfolio index, which is Y, right? So in other words, we are basically looking at a capital asset pricing model framework, right? So this will be the scatter plot of the data, and there's a positive, approximately linear relationship between X and Y. But there's only like 5 observations to base this conclusion on. So if we were to plug the 5 observations in the formula for alpha hat and beta hat, right, the OLS formulas, it gives you this particular output. Y hat, which is the dependent variable, is equal to negative 1.74, which is your alpha value plus 1.64 times X. 1.64 is the value of beta hat. And that brings us right back to this. This is how you compute it. Okay? And remember, this is your regression equation, but we don't have to compute the error term. So this is what our regression equation would be, where X is the excess return on the market portfolio over the risk-free rate, right? RM minus RF, also here known as the risk premium, market risk premium, okay? So as I indicated earlier, this is your X variable. Okay, so if an analyst tells you that she expects the market to yield a return 20% higher than the risk-free rate next year, what would you expect the return on fund XXX to be? So if the market is yielding a return that's 20% higher than the risk-free rate next year, in other words, this X variable will be 20% because the market yields a return 20% higher than the risk-free rate. That means the market return, right, RM, is 20% higher than the risk-free rate. So the difference between the market return and the risk-free rate is 20%. So if she expects the difference to be 20%, or then what would you expect the return on fund triple X to be? So in other words, you have the regression equation here. What you do, you plug this X variable, you plug this 20% for X, and the solution would be Y is equal to negative 1.74 plus 1.64, right, times the value of X. You plug that in, right, it's 20%, and you end up, when you work it out, the entire thing, you get 31.06. So that means for an expected market risk premium of 20%, given its riskiness, fund triple X would be expected to earn an excess over the risk-free rate of approximately 31%. Okay? So when you have a market risk premium of 20%, it means that this fund triple X, right? The fund triple X is going to earn an excess over the risk-free rate, meaning portfolio risk premium, right? Because remember we said that this is the market risk premium, this is the portfolio risk premium, okay? Meaning the excess return that you earn above and over the risk-free rate, right? The return on the portfolio minus your risk-free rate. So that's the excess return then on the portfolio. So an expected market risk premium of 20% means that the fund will earn an excess over the risk-free rate or a risk premium on the portfolio of approximately 31%. Okay, so this regression beta is the CAPM beta. So that means for the CAPM beta is just going to be 1.64, which we worked out here. And 1.64 means that the fund is risky, because the higher the beta, the riskier the fund. Okay, as you would appreciate from your previous finance courses. Now, the coefficient estimate of 1.64 for beta is interpreted as saying if X increases by 1 unit, Y will be expected, everything else being held equal, to increase by 1.64 units. Okay? So in other words, if X were to increase by 1, then Y will increase by 1.64. That's what the regression equation tells us. Okay? So of course, if beta hat was negative, a rise in X would mean a fall in Y, an average, a fall in Y. So if this were negative 1.64, if you worked it out and it wasn't plus 1.64, if it were minus 1.64, then that means that will be a negative 1.64. So that means a 1 unit increase in X causes a reduction in Y by 1.64. But that's if this were negative. It's not, it's positive. So 1 unit increase in X causes Y to increase by 1.64. Of course, in reality, you don't conduct a regression analysis using only 5 observations, right? So what are the assumptions underlying the classical linear regression model? Remember, the regression model is given by yt is equal to alpha plus beta xt plus ut. Okay, the assumptions are that the expected value of the error term is going to be equal to 0, meaning, or the error term has a 0 mean, right, and a constant variance, right? The variance of the errors is constant and finite over all values of x. Okay, and that the covariance will be equal to 0. The covariance of the error term I and the error term j, for our error term at point I or time I, the error term at point j is going to be equal to 0. So the errors are linearly independent of one another. The covariance, right, of the error term at time t and the corresponding x variable is also equal to 0. So there's no relationship between the error and the corresponding x variable. And the error term is normally distributed with a mean of 0 and a variance of sigma squared. So these are the assumptions of the classical linear regression model. Right? And an alternative to this particular assumption, assumption 4, is that the x's are non-stochastic or fixed in repeated samples. Okay? Now, once 1 through 4 holds, then that means that the OLS estimators of alpha and beta, meaning alpha hat and beta hat, are known as the best linear unbiased estimators. In other words, the blue, right? And remember we say beta hat is an estimator. This is an estimator. Beta hat is an estimator of the true value of beta, right? It's linear because beta hat is a linear estimator. It's unbiased because on average, the actual value of alpha hat and beta hat will be equal to the true values, okay? And best meaning that it has a minimum variance among the class of linear unbiased estimators. And this is where the Gauss-Markov theorem proves that the OLS estimator is the best. But we're not going to go into all of that at this point. And also, the OLS estimate must also be consistent, meaning the estimates will converge to their true values as the sample size increases to infinity. So the larger the sample, as it goes to converges to infinity, as it goes to infinity, larger it gets. That means the estimates will converge to their true values or their actual values. So you want larger samples generally for conducting OLS analyses. If it's unbiased, it also means that the expected value of alpha is going to be equal to alpha hat is equal to alpha, and the estimate of beta is beta, which is beta, estimate of beta hat is going to be equal to beta. So on average, the estimated value will be equal to the true values. Okay, and if it's efficient, it means the estimator beta hat of parameter beta is said to be efficient if it is unbiased and no other unbiased estimator has a smaller variance. If the estimator is efficient, then we are minimizing the probability that is a long way off from the true value of beta, meaning that the variance of beta hat, the variation or the variance between beta hat and beta is very, very minimal compared to any other unbiased estimator. It has the smallest variation between beta hat and beta. Because remember, beta hat is not necessarily the actual, is not the actual value of beta. You are estimating beta using beta hat. So that's why you call beta the estimator. But you want the variation or the variance between beta hat and beta to be as small as possible. Now we come to what's known as standard errors. So any set of regression estimates of alpha and beta, the alpha hats and beta hats, now they will be specific to the sample used in the estimation. Remember, you would have the population, right? And from that population, your data will be based on a sample of that entire population. But of course now, if you have a different sample, you have one particular sample, and that based on that sample, you get your estimates of alpha hat and beta hat. But then you have a different sample from that same population, right? Obviously, you're not going to get the same estimates of alpha hat and beta hat. You'll get different ones, okay? So the different data points of xt and yt will give you different values of alpha hat and beta hat, the OLS estimates. But it's important to know, or useful to know, whether one can have confidence in the parameter estimates. Because remember, one sample is giving you different estimates of alpha and beta compared to another. But are they going to vary by much? That's where these standard errors come in. You want standard errors as low as possible, and if they're quite low, it means that the values of alpha and beta, the estimates of alpha and beta, which are alpha hat and beta hat, are not going to be that different from the estimates that you would get from a different sample from the same population. Okay, so this estimate of precision of alpha and beta are given by the standard error. And just for illustration purposes, this is how you calculate the standard errors of alpha and beta. Okay, but of course, eViews gives it to you when they give you the output of the regression. Now, some comments on the standard errors. The larger the sample size, which is t, the smaller will be the coefficient standard errors. So you want the sample size to be as large as possible. And S squared, which is the estimate of the error variance, the larger this quantity is, the more dispersed are the residuals, and therefore the greater the uncertainty of the model. Now we come to hypothesis testing. So we want to make inferences about the likely population values from the regression parameters. Okay, So let's say you have this regression results. Y hat is equal to 20.3 plus 0.5091x, where this is your alpha hat value and this is your beta hat value. Okay, so beta hat is 0.5091, is a single point estimate of the unknown population parameter beta. Now, how reliable is this beta estimate? So the reliability of this point estimate, or the coefficient estimate, is measured by the coefficient standard error. Now, it might be of interest to answer the question, is it plausible, given this estimate, that the true population parameter beta could be 0.5? And the answer is obtained by hypothesis testing. So you want to see how reliable this value is, and is it plausible that this estimate is as close as very close to the actual population parameter beta. In other words, the beta for the entire population, because this is the beta hat for a sample of your population. Okay, the answer is obtained by hypothesis testing. So you have two hypotheses, the null and the alternative. Null hypothesis is HO and the alternative is H1. The null hypothesis is the statement or the statistical hypothesis that is actually being tested, and the alternative represents the remaining outcomes of interest. Okay, so let's say we are interested in the hypothesis that the true value of beta is 0.5, right? So what you do, remember, we got beta had to be 0.5, so we want to test the hypothesis that this is indeed the true value or is statistically significant, as we say. So beta is 0.5, and the null hypothesis is that beta is equal to 0.5. The alternative is that beta is not equal to 0.5, and this is known as a two-sided test. Okay, now we could have some prior information that we'd expect beta to be greater than 0.5 or rather than less than 0.5. So in this case, we would do a one-sided test, right, where the null hypothesis is that beta is equal to 0.5. The alternative is that beta is greater than 0.5, or you can have it the other way around. Beta is less than 0.5. So you have two ways to conduct a hypothesis test. You can look at the significance approach or the confidence interval approach. But for this course, we want to see the significance approach. Okay, so we are assuming that the error term is normally distributed with a mean of 0 and a variance of sigma squared, right? And this variance is constant. Now, since the least squares estimators are linear combinations of the random variable, right? That is, the estimator of beta or beta hat is the sum of Wt times Yt. Then the weighted sum of random variables is also normally distributed. So alpha hat will be normally distributed with a mean of alpha and a variance of alpha. A mean of alpha, and the variance will be variance alpha, right? Beta hat will be normally distributed, same thing. What if the errors are not normally distributed, right? Then will the parameter estimates still be normally distributed? And yet, if the other assumptions of the classical linear regression model hold that we looked at earlier, and the sample size is sufficiently large. So the standard normal variates can be constructed from alpha hat minus alpha divided by the square root of the variance of alpha, which is normally distributed with a mean of 0 and a variance of 1. And similarly, you have beta hat minus beta, which is divided by the square root of the variance of beta, again normally distributed with a mean of 0 and a variance of 1. Now, the variance of alpha and the variance of beta are unknown. So you have alpha hat minus alpha divided by the standard error of alpha hat, right? And then you also have, which has it approximately, which can be approximated by a t distribution, okay? And then you have beta hat minus beta divided by the standard error of the beta hat or the beta estimator. Now we know that this is our regression equation, right? How do we and what we're interested in is doing a test of statistical significance. In other words, we are testing the null hypothesis that beta hat is equal to 0.5 versus beta is not equal to 0.5. So to do that, we have to create a test statistic. The test statistic for beta, for example, will be beta hat minus beta star divided by the standard error of beta hat, where beta star is the value of beta under the null hypothesis. Then we get some tabulated distribution, which to compare the estimated test statistics. And the test statistics derived in this way can be shown to follow a t distribution with t minus 2 degrees of freedom. So as the number of degrees of freedom increases, we have to be we will be less cautious in our approach, since we could be sure that the results are robust. And we also need to choose a significance level denoted as alpha. This is sometimes called the size of the test. Normally you would use a significance level of 5%, right? But in practice it's 1%, 5%, 10%. If the test statistic is greater than the 5% significance level, then we can we could denote that it is statistically significant. So this is what a two-tailed test versus a one-tailed test looks like. Okay, a two-tailed test, and this is normal distribution, or approximately normal distribution, and at a 5% level, because it's two-tailed, it'll be 2.5% rejection region here. So this area under the curve, the unshaded area, is the 95% non-rejection region. Okay, if it's a one-tailed test, then here one end will just be 5% rejection region. Here's the non-rejection region. Similarly for this diagram also. Okay, so the difference with the normal distribution and the t distribution, right? They both look similar. The normal distribution is a bell shape, like we would have seen just now. And we can scale a normal variate to have zero mean and unit variance by subtracting its mean and dividing by the standard deviation. Okay, but there's a specific relationship between the t distribution and the standard normal distribution. Both are symmetrical and centered around zero, but the t distribution has another parameter, it's degrees of freedom. Okay, and we will always know this for the time being from the number of observations minus 2. In the limit, a t distribution with an infinite degrees of freedom is a standard normal, right? So when you go to when you have an infinite number of degrees of freedom, meaning the larger the population gets, the t distribution can be approximated by a normal distribution. Okay, right. So at the 5% significance level for normal distribution, the critical value is 1.64. For t distribution with 40 observations, it is 1.68, and with 4 observations, it is 2.13. Okay. Sorry, this is not number of observations, degrees of freedom. A 2.5 level is 1.96, and a 0.5 level it is 2.57. In practice, we rarely go with the normal distribution here, especially for OLS, ordinary least squares. So both are a bell curve, but the normal distribution peaks higher than the t distribution. So for the t distribution, the smaller the sample gets, the more difficult it becomes to reject the null hypothesis. Okay, so we're using the regression results that we had before, where this is your alpha estimate and this is your beta estimate, and again this means that a 1 unit increase in x causes y to increase by 0.5. Okay, these at the bottom here in parentheses are your standard errors. Okay, so we are testing null hypothesis that beta is equal to 1 against a two-side alternative. So the first step is to calculate the critical value. What is our critical value? Now, if we're going with a t distribution, it will be t with the degrees of freedom 20 to 22 minus 2, which gives us 20 at the 5% level. And you get the critical value as negative 2.086 and positive 2.086. Okay. Now remember, the null hypothesis is beta is equal to 1. The alternative is beta is not equal to 1. So our test statistic, the test statistic will be beta hat minus beta star, which is beta's whatever the null hypothesis is testing, beta is equal to 1. Right? So it's and we got beta hat to be from the regression equation as 0.5091. So it's 0.5091 minus 1 divided by the standard error of beta hat, and we saw that standard error is 0.2561. So divide by 0.2561 to give us negative 1.917. Now we know that the critical value is 2. Well, in this case, is a negative figure, so it's negative 2.086, right? And negative 1.917 exceeds negative 2.086. So that'll be in this region here, the non-rejection region. So we fail to reject. We do not reject the null hypothesis that beta is equal to 1, right? Since the test statistic lies in the non-rejection region. Okay? If we wanted to use that 10% size of the test statistic will remain the same. The only thing that changes is the critical t value, which becomes now negative 1.725. Okay? So the test statistic lies now within the rejection region because it's 1.9. 1.9 lies somewhere here. Negative 1.9 lies somewhere here because that's less than negative 1.725, right? So in this case, if you use the 10% level, you will reject the null hypothesis. Okay? So the T ratio, the formula for the testing the significance approach, the test of significance approach to hypothesis testing using a t-test was beta hat I minus beta star I divided by the standard error of beta hat I. Okay? So if the test is that beta I is equal to 0 versus beta I is not equal to 0, what this is that beta I is not statistically significantly different from 0, or in other words, not statistically significant, versus beta I is statistically significant, or in other words, it is statistically significantly different from 0. So in that case, our test statistic would be beta I, or the coefficient, the actual beta coefficient, right, divided by the standard error of beta I. Okay? So there's no minus 0 here because, I mean, it is 0, right? So you don't necessarily have to put minus 0, as before we had minus 1. Okay? So this is typically what we use for the test statistic. Now this is known as the T ratio or your test statistic, right? And this is what you typically use in regression analysis. This is the most important. This is the equation here that you most normally use in regression analysis to test to see whether the coefficient, the beta coefficient or beta hat, is statistically different from 0, or it is statistically equivalent to 0, meaning if it is statistically significant or not. Okay? Now let's say we have the coefficient of 1.1 with a standard error of 1.35 and a T ratio of 0.81. Okay? And you have another example where the coefficient is negative 4.4. The standard error is 0.96, right? So in this case, negative 4.4 divided by a standard error of 0.96 give you a test statistic or a T ratio of negative 4.58, right? In this case, 1.1 divided by 1.35 gives you a T ratio of 0.81. Now, this is we want to test now. We wanted to test this for statistical significance, meaning we want to see whether beta 1 is equal to 0 or beta 2 is equal to 0. Right? These are the two null hypotheses for this one and that one. Okay, we call this beta 1 and this is beta 2. Okay, and this is the for 5% level, a two-tailed test, 2.179. Okay, is the critical value. So for this one, the critical value is 2.179. Okay, 2.179, this is 0.81. 0.81 is much less than 2.179. That means it will lie within the non-rejection region. Once it's less than, the test statistic is less than the critical value, it lies in the non-rejection region, so you do not reject. Right? You do not reject. We do not reject the null hypothesis. Okay? But this one, negative 4.58, lies within the rejection region, because then if a two-tailed test, this will become now negative 3.055, right? So anyway, let's say this one negative 3.055, right? Let's say this one negative 3.55. Then of course the statistic would lie negative 4 would be here. So we would reject the null hypothesis that beta 2 is equal to 0. So this would be statistically insignificant, because we don't reject the null hypothesis. It's equal to 0, statistically speaking, of course. This, however, is statistically significant, okay? Because we reject the null hypothesis that beta 2 or negative 4.4 is equal to 0, okay? Now let's look at a finance example. We want to test for the presence and significance of abnormal returns, right? The Jensen's alpha, right? Written by a paper. This is something very common in finance. Use the Jensen's alpha. The data is the annual returns on the portfolios of 115 mutual funds from 1945 to 1964. Okay, so it's annual data then for 115 mutual funds. So the model is y is equal to alpha plus beta x plus u. Okay, again, y is equal to alpha plus beta times x plus u. That's the regression equation, where y is equal to the returns on portfolio J, right? J at time t minus the returns on minus the risk-free rate of return. Okay. Right. And here you have the market x variable is the market rates of return minus the risk-free rate of return. Okay. Right. And this is for J is equal to 1 to 115 mutual funds. Now we are interested in the significance of alpha. And the null hypothesis is that HO alpha is equal to 0. So let's look here. Now, according to Jensen's paper, a positive and significant alpha J for a given fund would suggest that the fund is able to earn significant abnormal returns in excess of the market required return for a fund of its given riskiness. And this alpha has been known as Jensen's alpha. So we don't have the results for all 115 mutual funds, right? But this is giving us the average of the alpha values calculated and the beta values calculated for the funds, right? Now the average of the alphas was negative 0.11 and negative 0.009. And what that means is that because both of them are negative, it tells us that on average the average fund was unable to beat the market because it recorded negative alphas in both cases. But looking at this, the minimum and maximum value, the maximum value is 0.058. So it means that some funds did manage to perform significantly better than the expected, significantly better than what was expected given their level of risk, with the best fund of all yielding an alpha of 0.058, right? Now the average fund had a beta of 0.840, and that means that in the CAPM context, the capital asset pricing model context, most funds were less risky than the market index, okay, because the market index has a beta of 1. So that means if the beta on average is less than 1, then that means it's on average less risky than the market. And that might be attributable to the funds investing primarily in mature stocks or blue chip stocks rather than small cap stocks, because blue chip stocks tend to be less risky. Okay, now the most visual method of presenting the results obtained is by plotting the number of mutual funds in each of the T ratio category for the alpha coefficients. Okay, and this is what we have here. We won't go into detail for that. The most appropriate, from the paper, the most appropriate critical value for the two-sided test of whether the alpha j is equal to 0 is approximately 210. Okay, that's the critical value, assuming 20 years of annual data, which gives you 18 degrees of freedom, because the degrees of freedom using the t distribution will be 22. The population, sorry, will be 8, will be 20, which is the sample size, minus 2, so you get 18. Only 5 funds have T ratios greater than 2. According to this, only 5 of the mutual funds here have T ratios greater than 2, right? And are therefore implied to have been able to outperform the market before the transaction costs are taken into account. Okay, right. When transaction costs are taken into account, only one fund out of 115 would be able to significantly outperform the market. Okay, so this is, there's an error here. This is not supposed to be gross of transaction costs. This is supposed to be net of transaction costs. So after taking into account transaction costs, only one fund was able to beat the market, or to outperform the market. However, 14, which is just 10 plus 1 plus 3, significantly underperformed the market compared to the market. Okay, now given a nominal 5% two-sided size of test being used, one would expect 2 or 3 funds to significantly beat the market alone. But it could be concluded that during the same period studied, the US fund managers appeared unable to systematically generate positive abnormal returns. And positive abnormal returns in this case means anything once they abnormal returns, it means significant returns. It can be significantly positive, meaning very high returns, or significantly negative, meaning losses. Okay, right, and that's it for this very first topic.